Hello guys, in this video I'll be talking about IR spectroscopy, and my name is Vyvyan. I'm doing PhD from UNSW Sydney, Australia, and you are watching my YouTube channel Kemistry, where I have uploaded more than 105 videos related to organic chemistry and various areas of research. So you can find number of playlists on my YouTube channel regarding organic chemistry, such as spectroscopy, IR spectroscopy, UV visible spectroscopy, NMR spectroscopy, retrosynthesis, name reactions, organic chemistry, general organic chemistry tutorials, where I have uploaded videos about how to apply for PhD, how to gain scholarships, how to write a paper, and how to do references, and so many other things. So please have a look on my channel if you can find number of interesting videos. But in this video we will be discussing about IR spectroscopy, and previously I have made a number of videos about IR spectroscopy. If you are a beginner, if you don't know what is IR spectroscopy, please go and watch my previous videos on this channel. Let's start from this table. And by the way, if you want to know from where I am following this, or which book I'm using, so I'm using the book of spectroscopy written by Pavia, so that is Pavia, a book written by Pavia. It's an introduction of spectroscopy, a simplified correlation chart, and I'll be giving you guidelines that how to identify or how to assign a peak in IR spectroscopy. So you try to memorize this table, and if you want to learn about the principle of IR spectroscopy, basics of IR spectroscopy, then please go back and watch my previous videos. But in this video I'll give you the clear and easy identification points for organic functional groups or bonds that you can identify them relatively quickly. Okay, let's start with the CH bond. How can you characterize a CH bond in IR spectroscopy? Or how can you classify that this CH bond is because of alkanes, or because of alkenes, or because of aromatics, or because of alkynes, or because of aldehydes? So how will you recognize this CH bond? Now this CH could give you type of vibration, maybe stretching, bending, stretching, out of plane, bending, stretching, out of plane, and stretching. Now, as you know that this CH bond is present in alkanes, alkenes, aromatics, alkynes, and aldehydes. Now, the type of bond is same, but it is different in different functional groups. So how we will be able to identify? Now, if you see a peak in IR spectroscopy first at around 3000 to 2850 in this region, in this range, and the intensity of peak is strong, S for strong, M for medium, and W for weak, then that peak can be assigned to CH bond, which is attributed with alkanes. Easy. Now I repeat again. If you see a peak in the range from 3000 to 2850 per centimeter, then you can easily assign this peak to a CH bond, and the intensity of peak should be strong, and we will say that this CH peak is present in any alkane. How will you characterize a CH3 group in IR spectroscopy? So the peak for CH3 group appears at 1450 and 1375. So if you see a peak at 1450 or 1375 and the intensity of that peak is medium, then that could be because of this methyl group. How can you identify or assign a peak to a CH2 group in IR spectroscopy? if you see a peak at 1465 and the peak intensity is medium, then we can safely say that this peak is due to the CH2 unit. How can you assign the CH bond present in alkenes? Okay, so if you have a CH bond present in alkenes, how we can assign that? So you look for a stretching in the region from 3100 to 3000, and if the peak intensity is medium, then this is due to the CH bond present in the alkenes. Now if you see the difference between CH present in alkanes and alkenes, that for alkenes it appears slightly higher, like at 3100, but for alkenes it appears slightly lower at 3000, and that is called out of plane bending. Or sometimes you see a OOP, out of plane bend, and along with this peak you will find a peak at 1000 to 650, and that will be the strong peak, and that we can safely say is because of the CH bond present in alkenes. Now how can you assign the CH bond in aromatics? It's a stretching peak. So if you see a peak at around 3150 to 3050 and the peak intensity is strong, then it is due to the aromatic aromatic bond, CH present in benzene or naphthalene or whichever. So this is the simplest rule or simplest thing to see in the but if there is a peak, how can you assign a CH bond in alkynes? So if you see a peak at around 3300, then it is due to the alkynes. But for aldehydes, the CH bond appears at around 2900 to 2800, or from 2800 to 27, and the peak intensity is weak. How can you assign a peak for CC alkane? It's not interpretively useful. How will you identify carbon double bond carbon, or how will you assign a peak for carbon double bond carbon in IR spectroscopy? So if you see a peak at around 1680 to 1600, we can say this peak is due to alkene. Or the double bond present in aromatics appears at around 1600 to 1475, and the peak intensity is either medium or weak. For triple bond, the peak appears at around 2250 to 2100, and that peak is assigned to alkynes. And for the carbonyl group aldehyde, the peak appears at around 1740 to 1720, and for ketones, peak appears at 1725 to 1705, and for the carbonyl group of carboxylic acids, it appears at around 1725 to 1700. For the carbonyl group present in ester, it appears at around 1750 to 1730. For the carbonyl group present in amides, it appears at 1680 to 1630. For carbonyl group present in anhydrides, this group appears at 1810 to 1760. The carbonyl group present in acid chlorides, it appears at around 1800. As you know that there's a carbonyl group in all of these functional groups: aldehyde, ketone, carboxylic acid, ester, amide, anhydride, and acid chloride. All of these functional groups share a one common feature, that they contain this carbonyl group. Now how we can identify that this carbonyl group belongs to aldehyde, and this carbonyl group belongs to ketone, this carbonyl group belongs to carboxylic acid, ester, amide, anhydride, or acid chloride? We can easily identify the carbonyl nature of the carbonyl group based upon IR spectroscopy. Here is the information. So again, if you see a peak at around 1740 to 1720, that is due to the carbonyl group present in aldehyde. If you see a peak at around 1725 to 1705, that is due to the carbonyl group present in ketones. If you see a peak at around 1725 to 1700, that is due to the carbonyl group present in carboxylic acid. But if you see a peak at around 1750 to 1730, that is due to the carbonyl group present in ester. If you see a peak at around 1680 to 1630, that is due to the carbonyl group present in amides. But if you see a peak at around 1810 to 1760, that is due to anhydrides. So anhydrides give you two peaks, one at 1810 per centimeter and another at 1760 per centimeter. But if you see a peak at around 1800, that is due to the acid chloride. Now one thing that is common, one thing that can be deduced from this information, that the carbonyl group present in acid chlorides appears at the highest frequency or wave number, and the carbonyl group present in amides appears at the lowest wave number. So amides, the carbonyl group of amides, this one appears lowest in wave number, and the carbonyl group of this acid chlorides appear highest at the wave number 1800. So this is how we can use IR spectroscopy to differentiate different functional groups based upon their characteristic peaks. Now let's characterize the carbon single bond oxygen that is present in alcohols, ethers, esters, carboxylic acids, and anhydrides. So carbon single bond oxygen bond is present in different functional groups, and this bond appears at around 1300 to 1000. And remember, in IR spectroscopy we have two regions. One is functional group region and another is fingerprint region. The functional group region starts from 1500 and goes all the way to 4000 per centimeter, whereas the fingerprint region starts from 1500 and goes all the way to 650. And if you want to characterize the carbon single bond oxygen that is present in alcohols, ethers, esters, carboxylic acids, anhydrides, then this bond gives you the peak at around 1300 to 1000, and the peak intensity is strong. How can you characterize OH bond in IR spectroscopy? And we have to look that OH group is present in alcohols, phenols, and carboxylic acids. And there are two things about OH group. One, it could be free. That means it's not bonded, or it's not showing any hydrogen bonding, or it's not hydrogen bonded. And second, that OH group is hydrogen bonded. So how we can differentiate between a free and hydrogen bonded OH group via IR spectroscopy? The free OH group, which is not bonded to anything, will give you a medium intensity peak at around 3650 to 3600, and the hydrogen bonded OH group will give you a peak at around 3400 to 3200, and the peak intensity will be medium. So the hydrogen bonding decreases the absorption frequency. So the hydrogen bonded OH group appears at around 3400 to 3200, whereas the free hydrogen bond or oxygen hydrogen bond appears at higher frequency, at higher wave number, that is 3650 to 3600. But the OH group present in carboxylic acids is all the way different than the alcohols and phenols, because it gives you a broad peak from 3400 to 2400. That is the easiest peak to be recognized in IR spectroscopy, because it has a big range of 1000 wave number. The OH group present in carboxylic acids gives you a peak from 3400 to 2400. So 3400 to 2400. And the peak intensity is medium. So this is how we can characterize or identify the OH group. How we can characterize or interpret NH bond in IR spectroscopy. First, we have to look that in which functional groups NH bond is present. It is present in primary amines, secondary amines, and amides. So it's present in 3 types of functional groups: primary amines, secondary amines, and amides. The stretching NH appears at around 3500 to 3100, and the bending peak for NH appears at around 1640 to 1550. Now, how will you characterize the CN bond that is present in amines? That bond appears at around 1350 to 1000, and the peak intensity is medium to strong. How will you characterize, or how will you determine, or how will you identify that the certain molecule contains carbon double bond nitrogen peak, and that sort of a bond is present in either in imines or oximes? So oximes and imines contain carbon double bond nitrogen functionalities, and this bond appears at around 1690 to 1640, and the peak intensity is weak to strong. How can you recognize the carbon triple bond nitrogen, that is nitriles? This bond is present in nitriles or cyanide, we can say, and this gives you the peak at around 2260 to 2240, and the peak intensity is medium. How will you characterize allenes, ketenes, isocyanates, and isothiocyanates? So the carbon doubly bonded with atom X and carbon doubly bonded with atom Y, and atom X and Y could be any group, and this sort of functional group functionality is present in functional group allenes, ketenes, isocyanates, and isothiocyanates, and the peak appears at around 2270 to 1940. So these functional groups give you a peak at around 2270 to 1940. Nitro group, nitrogen double bond oxygen, or NO2. This group gives you the peak at around 1550 to 1350. SH mercaptans, this gives you the peak at around 2250, and the peak intensity is weak. Sulfoxides, sulfur double bond oxygen, which is present in sulfones, sulfonyl chlorides, sulfates, and sulfonamides, and this bond, sulfur double bond oxygen, appears at around 1050 or 1375 to 1300. For sulfones, for sulfonyl chlorides, it appears at around 1350 to 1140. And how will you characterize alkyl halides through IR spectroscopy? The CX bond, and the X is halogen. It could be fluorine, chlorine, bromine, iodine. So if the X is fluorine, then you will see a peak in IR spectroscopy at around 1400 to 1000. And if the X is chlorine, then you will see a peak at around 785 to 540. But if the X is bromine or iodine, you will see a peak at around 670. And the peak intensity for all of these peaks is strong. These are the base values for absorption of bonds. For OH, the base value is 3400. For NH, 3400. For CH, 3000. For nitrile, it is 2250. For carbon triple bond carbon is 2150. For carbonyl, it's 1715. And for carbon double bond, 1650. And for carbon single bond oxygen is 1100. So what the base values means that mostly or generally these bonds give you peak at these frequencies. But depending upon where they are attached, in which functionality they are connected. The peak intensity and the shape varies depending upon which functional group they belong to. So these are the important numbers that I have mentioned so far in this video, and they will help you to recognize various functional groups in IR spectroscopy. And in the next video, we will be talking about how to approach the analysis of a spectrum, or what you can tell at a glance. That is our next topic in next video. I hope you like this video, and if you have any questions related to IR spectroscopy or generally organic spectroscopy, let me know in the comment section, or if you want me to make video about any topic that you want me to, or that you require to understand, or you want to understand, and then suggest me that topic, then I will make video on that topic. Once again, thanks for watching. Take care. Bye.